You don't have to think very hard about the world around you. It just presents itself. A floor under your feet, a chair that stays where it is, a table that doesn't flicker in and out of existence when you stop paying attention. Things feel solid, stable, located somewhere in space, and we grow up assuming that's simply how reality works. Objects have positions. They're there, whether anyone is watching or not. That assumption feels so obvious, we rarely even notice it's an assumption at all. But that confidence comes from living among large things. And when you start peeling reality down, past dust, past molecules, past atoms, something unsettling happens. The rules you were relying on quietly stop applying. To see why, imagine a very ordinary experiment. You stand in front of a wall with two narrow openings cut into it. Behind that wall is another surface that can record impacts. Now you start throwing small balls, marbles, pellets, anything solid, straight at the wall. Each throw is uneventful. The ball passes through one opening or the other. It hits the surface behind and leaves a mark. You repeat this over and over, hundreds of times, thousands. When you finally step back and look at the accumulated pattern, there's no mystery at all. Two dense regions of impacts appear, lined up neatly behind the two openings. One cluster for the left path, one for the right, exactly what you'd expect if every ball took one definite route. So far, nothing strange. Now keep the setup, keep the wall, keep the two openings, but change what you're throwing. Instead of marbles, you fire electrons. Electrons are unimaginably small, far smaller than anything you can see, but they're still detected in a very specific way. When an electron reaches the detector, it produces a single signal, one click, always one, never a fraction of a click, never a smear. They arrive as complete, indivisible events, discrete, localized. In that sense, electrons behave exactly like tiny particles, at least at first. But then we do the only thing you can do in physics. We stop talking and we start counting. Click after click, we mark the spots. We let the picture build itself. And when the pattern finally shows up, it isn't what any sane person would predict. It's not two piles. It's not left slit and right slit. It's bands. Bright and dark lanes across the screen. Heavy traffic here, almost nothing there, then heavy again, then empty again. A barcode, a zebra, a fingerprint made of gaps. That kind of pattern has a name. It's what waves do. With waves, you don't just get this way or that way, you get overlap. Two waves can stack up and make something bigger, crest on crest, or they can meet out of step and erase each other, crest on trough, leaving nearly nothing behind. That push and pull pattern is interference, like two sets of ripples on a pond crossing and drawing a shifting grid of calm lines and high peaks. So now we're stuck with an uncomfortable sentence. Electrons show up like particles, one click, whole and indivisible. But over time they arrange themselves like waves. Maybe you think they're interacting. Maybe the electrons are jostling each other on the way, like a crowd changing its shape. Fine, let's remove the crowd. We fire them one at a time. One electron, wait, click, mark it. Another electron, wait, click, mark it. Slow, boring, patient. And the same stripe pattern returns as if nothing changed. They never meet, yet the interference remains. So whatever is happening, it isn't electron on electron. It's something each electron is doing all by itself, which sounds ridiculous until you try to picture it. Maybe the electron splits, goes through both slits, and recombines on the other side. So we test that idea the honest way. We check the path. We place a detector at the slits, something that can tell us which opening the electron used. And now each electron behaves like a well-trained little projectile. Left slit or right slit. Always one, never both. A definite route. But when we step back and look at the accumulated hits on the screen, the stripes are gone. The barcode disappears. We're back to two plain clusters, one behind each slit, exactly like the marble experiment. So here's the rule you can't unsee once you've seen it. When there's no way to tell which slit the electron took, you get interference. When you gain which path information, the interference vanishes. And it's tempting to blame the detector. Maybe we shoved the electron around. Maybe we ruined the experiment with our clumsy measurement. So we try to be gentle as physics allows. But this is where Heisenberg steps in with the bad news. There is no perfect, gentle option. If your method is capable of revealing the path, it necessarily introduces the kind of interaction that destroys the delicate interference. And if you weaken the interaction enough to preserve the interference, you also erase the information. You no longer know the path. You don't get both. You don't get to keep the pattern and keep the story of which way it really went. Nature makes you choose. This has nothing to do with crude equipment or clumsy experiments. It isn't a problem waiting for better technology. The limitation is deeper than that. It's part of how nature itself is put together. An electron does not carry a well-defined route with it through the experiment. There is no hidden trajectory quietly waiting to be revealed. When you ask which path it took, you aren't uncovering an answer that was already there. You are forcing the situation into one that has an answer, and that raises an uncomfortable question. Before we looked, what was the electron doing? Was it split between both slits? Was it nowhere in particular? Was it exploring every possible route at once? The truth is, we don't have an answer to that. And more importantly, physics suggests the question itself may be misplaced. We're used to thinking in terms shaped by everyday life. Balls roll, doors open, objects occupy locations. Things move along paths from one place to another. That mental framework works because the world we interact with is made of enormous collections of particles, trillions upon trillions of them locked together. At that scale, all the quantum subtleties blur into something stable and predictable. But strip things down to a single electron, a single photon, and that familiar picture collapses. The concepts we rely on, position, path, location, stop behaving like solid ideas. They become approximations that no longer quite fit. So when someone insists, yes, but which slit did it really go through? The most accurate reply isn't, we don't know. It's that, without a measurement, the question doesn't have a meaning. That isn't a philosophical stance. It's the operational rule the experiments force on us. And whether that feels satisfying or deeply unsettling doesn't matter. Nature isn't interested in preserving our intuition. Now, here's the remarkable part. Despite all this strangeness, physics doesn't grind to a halt. We don't just shrug and give up. We calculate. And those calculations work astonishingly well. The price we pay is giving up certainty. Instead of predicting exactly what will happen, we predict likelihoods, probabilities. And the tool we use to do that sounds almost embarrassingly simple. We represent each possible way an outcome could occur with a little arrow. Each arrow has a size. Each arrow has a direction. To find the probability of an outcome, we combine the relevant arrows and then square the length of the result. That's it. No pictures of tiny balls flying along hidden tracks, just arrows added carefully, producing numbers that experiments confirm every single time. This is where the rules quietly change. When an outcome has more than one possible route, an electron slipping through the left opening or the right, we don't handle it the way common sense would suggest. We don't calculate each chance separately and add them up afterward. Instead, we combine the arrows first. And arrows don't behave politely. If two arrows happen to line up, tip to tail, they reinforce each other. The result is a longer arrow, which means a higher chance of that outcome showing up. But if they face in opposite directions, they work against each other. They shrink or even wipe each other out completely. The probability drops, sometimes all the way to zero. That push and pull is interference, and it's the reason those striped patterns appear on the screen. The arrow 4 came through the left slit, and the arrow 4 came through the right slit don't always agree. At some points on the detector they cooperate, at others they clash. The direction depends on where you're asking the question, where on the screen you're looking. But the moment you determine which slit the electron used, the situation changes. You no longer have competing alternatives. There's only one path in play, and with only one path, there's nothing left to combine. No opposing arrows, no cancellations, no interference, just ordinary probabilities added up the familiar way. The calculations themselves are almost embarrassingly straightforward. What's difficult isn't the math, it's living with what the math implies. Those arrows have a formal name, probability amplitudes, and they come with a twist that still feels wrong the first time you hear it. They aren't built from ordinary numbers. They involve imaginary numbers, values that don't sit anywhere on the number line. You can't measure them directly. You can't point to them in space. Yet when you square their lengths, the strangeness disappears. Out come clean, positive numbers, real probabilities, numbers experiments confirm with uncanny precision. So the structure of reality, at its foundation, is encoded in objects we never observed directly, expressed in mathematics that has no physical ruler, used to predict outcomes that are never certain, only likely. That's the quantum world. And if you're tempted to ask why nature chose this scheme, why arrows, why amplitudes, why this strange bookkeeping, the honest answer is unsatisfying. We don't know. There is no deeper story beneath it that physics has uncovered so far. The arrows aren't explained by something simpler. They are the explanation. Science doesn't always tell us why the universe is built the way it is. Sometimes it only tells us how it behaves. And if you keep pressing for deeper reasons, eventually you hit a hard floor, where the only answer left is that this is how nature operates. Now, the truly surprising part is that this isn't a special trick reserved for electrons and slits. The same logic shows up in places that look completely different. Take a beam of neutrons and aim it at a crystal. A crystal is nothing exotic, just atoms arranged in a repeating pattern, stacked neatly like fruit in a box. A neutron enters, scatters off one of the nuclei, and shoots off toward a detector at some angle. So which atom did the neutron actually hit? That's not an easy question, because the crystal isn't made of one target. It's made of many, hundreds, thousands of nuclei arranged in a precise repeating pattern. From the neutron's point of view, any one of them could have been responsible for the scattering. And crucially, once the neutron reaches the detector, there's no leftover clue pointing back to a particular nucleus. All those possibilities lead to the same final result. The alternatives are indistinguishable, and when physics can't tell the difference between alternatives, it forces us to combine them differently. We don't pick one and ignore the rest. We add all the amplitudes together. When we do that, interference appears. Certain scattering angles light up with sharp intensity, while neighboring angles go almost completely dark. A structured pattern emerges, remarkably similar to the double-slit experiment, except now it's as if thousands of slits are acting together. But the story doesn't end there. In some materials, alongside those sharp peaks, there's also a faint haze, neutrons scattered in nearly every direction, filling in the gaps. Something else is happening. The missing piece is spin. Neutrons carry spin, and so do the nuclei in the crystal. Occasionally, during a collision, the neutron flips its spin, and when that happens, angular momentum has to be conserved. One of the nuclei must flip as well. Now, the situation changes. If a nucleus flips its spin, it leaves a mark, at least in principle. That particular nucleus is now different from all the others. Even if no one checks, the information exists. The alternatives are no longer identical. And once the alternatives become distinguishable, interference disappears. We stop adding amplitudes and start adding probabilities. The result is no longer a crisp pattern, just a smooth spread of scattered neutrons in every direction. So you see the pattern emerging. When the neutron scatters without flipping any spins, there's no way to know which nucleus was involved. The paths blur together and interference survives. When a spin flip occurs, the path can, in principle, be traced back to a specific atom. The blurring vanishes. So does the interference. The rule never changes. If different possibilities cannot be told apart, even in principle, you must combine their amplitudes. If they can be told apart, even if no one actually checks, you treat them separately and add probabilities instead. That distinction doesn't depend on curiosity or choice. It depends on whether nature itself keeps a record. Follow that rule, and the experiments line up perfectly. Ignore it, and nothing makes sense. Now the story takes a turn, because all this quantum oddness isn't just an abstract puzzle. It isn't something confined to chalkboards and labs. It reaches all the way up to you, literally to the fact that you're here at all. There's a principle at the center of this, one you've almost certainly heard named before, the uncertainty principle, and it's usually misunderstood. People often think it's a comment on our limitations, that we simply lack the precision or the craftsmanship to measure things accurately enough, as if, with better tools, the problem would disappear. That's not what it says. The uncertainty principle isn't about imperfect measurements. It's a statement about how nature behaves, even in principle. It draws a line no technology can cross. What it tells us is this: a particle cannot simultaneously possess a sharply defined position and a sharply defined momentum. Not because we're careless, not because we disturb it too much when we look, but because those two properties aren't both well defined at the same time. To see why, imagine trying to pin an electron down. You squeeze it into a very tiny region of space, so you know exactly where it is. For a moment you succeed. Its position becomes clear. But something else gives way. Its momentum becomes uncertain. The electron doesn't sit calmly in place. It begins to jitter, its motion growing more erratic the tighter you try to confine it. And the relationship cuts both ways. If you instead prepare an electron with a very precise momentum, moving smoothly, predictably, its position spreads out. It refuses to be localized. It could be almost anywhere. This isn't an arbitrary rule. It comes from the mathematics of waves. A perfectly regular wave, extending endlessly, has a very clean wavelength. You can measure it exactly, but try asking where that wave is located, and the question falls apart. It's everywhere at once. There's no single spot you can point to. Now take the opposite case. A short pulse, a compact ripple. You can say exactly where it is, but its wavelength becomes ambiguous. It's no longer a neat repetition. It's a mixture of many wavelengths blended together. That's the trade-off. Spread out in space, and the wavelength sharpens. Concentrated in space, and the wavelength dissolves. Quantum mechanics connects wavelength directly to momentum. Shorter wavelength means greater momentum. Longer wavelength means less. So the wave trade-off becomes a momentum position trade-off automatically. It isn't imposed, it emerges. And now comes the consequence that changes everything. Consider an atom. At its center is a positively charged nucleus, with electrons bound to it by attraction. Classical physics predicts disaster. An electron moving around a nucleus should radiate energy, slow down, spiral inward, and crash into the center almost instantly. Atoms should self-destruct. Matter should never hold together. But atoms are stable. Always have been. And the reason traces back to uncertainty. If an electron tried to sit right on top of the nucleus, its position would be exquisitely precise. And that precision would force its momentum uncertainty to explode. The electron would carry enormous kinetic energy, violently unstable. It can't remain there. Uncertainty pushes it outward. But it can't drift away either. The electrical attraction pulls it back in. What emerges is a compromise, not a point, not a wide orbit, but a region, a cloud of probability, a stable balance between confinement and motion. That region has a characteristic size, about 1/10,000,000th of a meter. That scale defines the size of atoms, and from that scale flows chemistry, biology, and everything built from them. Without the uncertainty principle, electrons collapse. Without electrons in stable atoms, there are no molecules. Without molecules, there is no chemistry. Without chemistry, there is no life. You are here because uncertainty refuses to let matter collapse. And it doesn't stop there. The same principle is quietly at work right now, holding you up, keeping your feet from passing straight through the floor beneath you. When you're standing on solid ground, nothing dramatic seems to be happening. Your shoes press against the floor presses back, end of story. But zoom in far enough, and something remarkable is going on. The atoms in your shoes are being brought very close to the atoms in the floor. Push them closer still, try to compress them into a tighter region, and the electrons inside those atoms begin to protest. Not emotionally, not intentionally, but inevitably. Forcing them into a smaller space sharpens their positions, and that sharpening comes at a cost. Their motion becomes increasingly erratic. They jitter, they surge, and that restless motion pushes outward. That resistance is what you call solidity. Hardness isn't a classical property at all, it's a quantum one. In a purely classical universe, charges would arrange themselves as efficiently as possible. Positive and negative would collapse together. Everything would sink inward until matter piled up into a single dense point. There would be no rigidity, no structure, no surfaces to stand on. Quantum mechanics forbids that outcome. You can't squeeze particles indefinitely without paying for it in momentum and energy. Nature enforces the bill. So when a chair supports your weight, when the floor holds firm beneath you, you're feeling the consequences of that rule. You're not hovering above the earth by accident. You're being held up by uncertainty. Now let's turn to another assumption classical physics once made and got completely wrong. Energy in everyday life feels smooth, continuous. You can add a little, get a little effect. Add more, get more effect. There's no sense of preferred amounts. Everything blends. At the scale of atoms, that smoothness vanishes. Energy comes in discrete packets, not a ramp, but a staircase. You don't slide between values, you jump. A familiar analogy helps here. Think about a stretched string on a musical instrument. When you pluck it, it vibrates, but only in certain ways. There's a lowest note it can play, then a higher one, then another. You don't get every possible pitch in between. Only specific patterns fit. Electrons behave the same way. The electron's wave must arrange itself around the nucleus in precise patterns. Most patterns simply don't work. The ones that do each come with a specific energy. These are the atom's allowed energy levels. If an electron occupies a higher level, it doesn't gently slide down. It has to make a jump. And when it does, the excess energy doesn't disappear. It leaves as light. A photon carries away exactly the difference between the two levels. Not close, exact. Because those energy gaps are fixed, the photons have fixed energies. And photon energy determines color. That's why different atoms glow in different hues. Hydrogen emits one set of colors, helium another. Sodium produces that unmistakable yellow-orange light used in street lamps. When we analyze the light from distant stars, we find missing colors, dark lines carved out of the spectrum. Those absences are signatures, atomic fingerprints. From them, we can tell what stars are made of across unimaginable distances. All of that, astronomy, chemistry, light itself, rests on the fact that atomic energy is quantized. And then there's a rule even stranger. Electrons refuse to share states. Place multiple electrons into an atom, and they don't all sync to the lowest energy arrangement, even though that would seem efficient. Instead, Only a limited number can occupy the same configuration. Once that space is filled, additional electrons are forced into higher levels. This rule is known as the Pauli exclusion principle, and while we can describe it precisely, its deeper reason remains elusive. It isn't derived from common sense. It's a rule nature insists on. Without it, chemistry collapses. Every atom would behave nearly the same. Carbon would lose its personality. Oxygen would be indistinguishable from iron. The periodic table would flatten into monotony. But because electrons are compelled to spread out, to occupy different states, atoms develop structure. Structure creates diversity. Diversity creates chemistry. The world owes its variety to a refusal. Electrons simply will not all do the same thing. Why 2 per state? Why not 3? Why not 10? There's no satisfying answer. These are the terms nature sets. Our task isn't to negotiate them. It's to discover them and to learn how far they carry us. So where does this trail actually lead us? We began with a question that sounded simple enough. What is reality? And along the way, we discovered that answering it required dismantling almost every assumption we started with. At the smallest scales, particles don't sit at fixed locations waiting to be found. They don't trace clean paths from place to place. Instead, they're described by overlapping possibilities, combined through mathematical rules that predict likelihoods rather than certainties. There are limits to what can be known. Not because we lack cleverness, but because nature itself refuses to be fully pinned down. That realization unsettles people. It always has. Some of the greatest physicists who ever lived were deeply uncomfortable with it. Many spent decades searching for a hidden layer beneath the uncertainty, some underlying machinery that would restore clarity and determinism if only we could uncover it. So far, no such layer has revealed itself. Every experiment that probes deeper ends up reinforcing the same picture. The fuzziness doesn't go away. The probabilities don't dissolve into hidden certainties. There is no secret clockwork ticking beneath the surface. Naturally, this invites another question. If particles don't carry definite properties until we measure them, then what are they doing in the meantime? And here, physics gives an unusually honest answer. It doesn't know. The theory doesn't describe an unseen movie playing behind the scenes. It provides rules for connecting preparations to outcomes, for predicting what will be observed when an experiment is performed. Beyond that, it stays silent. Different people fill that silence in different ways. Some imagine particles existing in many states at once. Others picture branching universes where every possibility unfolds. Still others argue that the question itself is misguided, that physics should speak only about observations, not unseen processes. These viewpoints disagree philosophically, but they agree mathematically. Every one of them makes the same predictions, and no experiment so far can tell them apart. What can be said with confidence is this: the framework works. The theory describing how electrons interact with light, quantum electrodynamics, has been tested with astonishing precision. Certain quantities can be calculated to extraordinary accuracy, and when those numbers are checked in the lab, they line up digit for digit. Nothing else in science has been scrutinized so finely, and nothing else has held up so well. So whatever reality looks like behind the curtain, the rules we've uncovered are reliable. They predict outcomes. They explain patterns. They connect theory to experiment with uncanny success. And look at what those rules account for. They explain why atoms are stable, why matter has structure, why different elements behave differently, why stars shine, why chemistry is possible, why your eyes can detect light, why your brain can think. Everything you've ever interacted with is built from particles obeying these counterintuitive principles. Yet none of it feels strange in daily life. The world appears solid. Objects stay put. Motions look smooth and predictable. That's because we're large. We're made of staggering numbers of particles acting together. At that scale, quantum effects blur into averages. Interference patterns become too fine to notice. Uncertainties shrink until they're negligible. The quantum layer never disappears, it's simply buried under abundance. So what have we learned? We've learned that nature is under no obligation to match our intuition. Our minds evolved to navigate a world of moderate sizes and speeds, to spot food, avoid danger, and move efficiently. They were not designed to grasp the behavior of electrons. And yet, remarkably, we figured it out anyway. That's the quiet miracle. Not that the universe is strange, but that arrangements of atoms like us manage to uncover the rules governing atoms themselves. We built experiments, we refined measurements, we wrote equations, and those equations describe reality with stunning accuracy. We still don't know why the rules are what they are. We don't know what, if anything, is happening when no measurements are made. We don't have a picture that feels intuitively satisfying. But we have something better than comfort. We have a framework that works. And that's what physics is, that's quantum mechanics. So when someone asks, what is reality? The most honest response is still, I don't know. What we can do is calculate what will happen when we interact with it. We can test those calculations. And again, they're right. Maybe the better question isn't what reality is, but how it behaves. That's a question experiments can answer. And when we pay attention, when we let nature show us what it does, instead of insisting it behave as we expect, we uncover something extraordinary. A world governed by interference and uncertainty, by entities that are neither particles nor waves, but something subtler. A world richer, stranger, and more inventive than our classical pictures ever allowed. And that, perhaps, is a fair trade for letting go of what once felt obvious. Nature, it seems, has no intention of making things easy for us.